So, I'm going to go through some of these questions, see how many we get through, but we'll just start at the very beginning. So the first one, these are all from last year's exam, and they all bear content relative to what we're working on at the moment, with a bit of a few outliers. So question 2 is introducing you to this idea of Benford's law. Now it's probably worthy of saying as well, right? I've taught you all of the content that's listed in the SACE subject outline, all right? So I can pull that up, I can show you, we've addressed everything. However, in the exam, one of the things that will pop up is comprehension. And so you'll read this and you go, I've never heard of Benford's law before. That's because it's not part of the course. The reason they're putting it in here is because it's about reading, understanding, and then solving the problem accordingly. All of the skills you have to solve this problem. All right, but one of them that they're testing is comprehension. Can you read this, understand it, and now solve the problem? So they introduce you to Benford's law, and then they've got a probability distribution table there, which we're very familiar with. And then they're asking a number of chapter 7 questions. So they're asking, why is it not uniform? Well, a uniform variable has all probabilities are the same. Okay, determine the probability of the leading number being 6 or greater, so that's the sum of these probable events, okay? The sum of 6 plus 7 plus 8. And then for part C, which formula would calculate the mean? Well, the mean of a probability distribution table is each event multiplied by its probability added together. So that would be the middle box. Okay, let's turn the page. So where we get into the relevant stuff is this one here. Benford's law can be used to detect fraudulent financial records. Further investigation of a company's financial records is undertaken if a calculated 95% confidence interval supports the claim that the mean of the leading digit of the financial records is greater than 3.441. So basically what they're checking for is, rather than people claiming $100, they claim things like $99 because they're trying to get just under that bracket that the AI system will detect. And so now they're testing the mean of the leading digit rather than having a cutoff limit. So consider a random sample of where are we up to? Consider a random sample of 250 numbers from a company's records. The mean of this leading digit is 3.816. Calculate a 95% confidence interval for the mean of the leading digit using the random sample described above. Assume the standard deviation is 2.462. So we're doing a sample confidence interval. Our confidence level is 95%. Our observed mean is 3.816. Our standard deviation is 2.462. And our number of samples is 250. So that's the syntax we're putting in our calculator for the mean of a sample, and we should get 3.51 is less than the mean is less than 4.12. Okay, so that's our confidence interval. Now, does the 95% confidence interval suggest that further investigation should be undertaken? So we've got two answers here. The first is to answer the question. It's yes or it's no, all right? Now, they're saying further investigation is required if the leading digit is greater than 3.441. Okay, based off the confidence interval, the lowest the leading digit could be from this sample is 3.51, which is larger than our 3.441. So the answer is yes, further investigation is required because the confidence interval is completely above the stated value of 3.441. That's probably the clearest way to say it. Yes, you get 1 mark for saying yes. All right, yes. Further investigation is required because the confidence interval is completely above the stated 3.441 value. The stated, not above the stated 3.441. All right. Any questions there? Okay, move on to the next one. And so here we have a normal distribution question leading into a little bit of the central limit theorem. So we have the fat content in per grams of Ted's oat milk can be modelled using this normal distribution. The mean is 2.7, the standard deviation 0.35. Determine the probability that a carton of Ted's oat milk will contain at least 2.8 grams of fat. So this is an NCD calculation. We're talking about the normal distribution. We're saying at least 2.8 grams. So the lower boundary 2.8, upper boundary infinity. Standard deviation is 0.35 and the mean is 2.7. All right, so that's what we're putting in our calculator. That's our syntax, and we evaluate that. I got 0.388. Okay, between 1 and 3 grams of fat, so the same thing, we're just changing the lower and the upper boundary. The standard deviation and the mean remain the same. And I got 0.8043. And so remember, one of the things I've always said is we should write, I can't remember what the third figure was there. We should, here it is, 0.3875 I had. We should write 4 figures and then round accordingly. Okay. Ted's oat milk is sold in packs of 6 cartons. Let S6 represent the distribution of fat content in one 6-pack of Ted's oat milk. Explain why S6 can be modelled by a normal distribution. So X is normal, all right, normally distributed. We're told that in the question, the fat content can be modelled using a normal distribution. X is normal, therefore Sn is normal for all n. Doesn't matter how small the n value is, Sn will be normal as well. Okay, on to part 2. Whenever you have a show that, you need to be very, very clear with the show that. Show that the distribution of S6 has a mean of 16.2 and a standard deviation of 0.857. So this is just from our formulas. The mean of S6 is equal to 6 times the mean of X, which is equal to 6 times 2.7, and that's your 16.2. All right, so being very clear how we arrive at that 16.2 value. The same with the standard deviation of S6 is the square root of 6 times the standard deviation of X, square root of 6 times 0.35, and we get that 0.857. Okay, very good. So we're calculating S6. Hence determine the probability that a 6-pack of Ted's oat milk will contain less than 18 grams of fat. So, using these properties, all right, we're now talking about the distribution of S6. So we're not talking about one oat milk, we're talking about 6 of them together, added up together, and we're saying what's the probability that 6 of them added up together are less than 18. So, our upper boundary is 18. All right, the highest this 6-pack can possibly be is 18. Our lower boundary, negative infinity. Standard deviation and mean are these values here. We're talking about the distribution of S6. We'll evaluate that and we get 0.9821, 0.982. So what this means is 98.2% of Ted's oat milk cartons have less than 18 grams of fat. All right, part C. Find the probability. Find the value of K, the probability of C being less than K is 0.99, given that Z is normally distributed with a mean of 0, standard deviation of 1. All right, so here they're talking about the Z distribution. All right, so we need to make sure we don't miss that. And they're saying, what's this value, K, such that the area here is 0.99. All right, so this is an inverse normal calculation. What do we have? We've got tail. All right, the tail is to the left, or you can look at which way is the arrow pointing. It's pointing to the left. The area is 0.99. Standard deviation 1, mean 0. We evaluate that. We get K is 2.326, 2.33. All right, now this one's quite tricky. There's 2 ways of doing this. All right. The label of the 6-pack says each pack contains less than 18 grams of fat. The company would like this statement to be true for at least 99% of Ted's oat milk 6-packs. All right, so So we saw it was 98.2, they want to put that number up to 99. It can't change the mean fat content of a six-pack, but these improvements could be made if the standard deviation can be reduced. All right, so they can't change the mean fat content, but they can make the distribution more narrow. They can decrease the standard deviation. So, using your answer to part C, determine the largest possible value of sigma of S6. That will result in at least 99%. All right, so what we've seen here is this z-score corresponds with 99%, right? And they're saying, how about this value here, 18 grams? We want that to correspond with this z-score. 18 grams corresponds with the z-score 2.33. All right, and so if we can write out the z-score formula, z is x take mu on sigma. We've got the z-score of 2.33. The result we're talking about is 18. That corresponds with the z-score of 2.33. The mean is 16.2, and we're saying, what are we changing that standard deviation to? And now it's just a linear equation. We'll swap these variables over. So we'll have sigma is 18 take 16.2, 1.8 on 2.33. And we'll evaluate that 0.7725. Okay. So that's the link they want you to make from part C with the z-score. All right, that's a little bit tricky to see. Another way you can arrive at the correct answer is through trial and error. Okay, let's steamroll on to question 8, unless there's any questions about that one. Now I'd like to get through 8 quite quickly. So question 8, again, it's combining binomial and normal distribution. We have a company produces a type of fruit-filled chocolate called chocolate. They are produced on an automated assembly line that can result in imperfect chocolate. The probability is 0.15 that it's randomly selected as imperfect using the binomial distribution. Okay, so part A is binomial question. What's the probability of 8 out of 80, 6 of them being imperfect or more than 20 being imperfect? Okay, so let's leave those, let's turn the page. All right, the manager of the assembly line can adjust the rate of production of chocolate resulting in a change in the probability that a randomly selected chocolate is imperfect. The probability can be modelled by this function. All right, where P of X, the probability, the y-axis, represents the probability that a randomly selected chocolate is imperfect, and X represents the rate of production. Graph P of X. Okay, now you need to make sure, whenever you have a graphing problem, right, you think, geez, graphs are easy, but you just need to make sure you do it properly, all right? It's worth doing thoroughly to make sure you get the marks. So I'll talk about how we do mark it when we're marking graphs in an exam, in a test. So the first thing is we've got the equation, sine of 0.00392 x squared plus e to the minus x. Now, we need to have our calculator set in radians. So the first thing to say is they give you the V window, all right? They're saying x min from 0 to 20, and the y goes from 0 to 1. All right, so you must have those values the same. Now, there's a few key features that we're looking for. We're looking for turning points, okay, or points of inflection. Roots, if they occur, we're not going to have any roots on ours. Asymptotes, these are the key features they're looking for when you have a graph. So when you graph it, the first thing that jumps out to you is it has this kind of shape. Okay, now it's not enough to just sketch the shape. What we're looking for, we can see there's a turning point here. All right, we can see there's a minimum. Straight away, you should be g-solving that minimum and drawing it in the corresponding box. So you g-solve the min, you see its x is 3.57 and y is like 0.13 or something like that. So you need to make sure that your minimum point occurs in the box with those properties. Generally, we have like a bit of a window where we'll accept it, but be precise. So the marks we awarded for the graph, like in the exam last year, you got one here, you got 1 mark for having both of these in the correct position, right? So both of them was worth 1 mark. And the third mark is for having some point of inflection along here somewhere. And so the point of inflection means it's changed shape, right? It's concave up to concave down. There are a number of students that forgot it and they just did something like this. All right, so if they're doing something like this, there's no point of inflection, it's going to be wrong. So that's how we allocated the marks for it last year, making sure each part's in the right spot. Okay, moving on. Using the function p of x, determine the possible rates of production that resulted in the given probability of 0.15 stated in part A. So remember, on the y-axis we have probability. On the x-axis we have rate of production. Now what they're saying, right, is the higher the rate of production, the more chocolate you're making per second or per minute, the more likely they are to be imperfect. You're rushing the machine, it's not getting the process properly. So we've got a probability of 0.15, and we're saying what's the corresponding rates of production? There are 2 answers. We want an x calc. Rate of production is on the x-axis. We're doing an x calc when the y value, the probability, is 0.15. So if we perform that, that's for part C, we get x is 2 or 6.15 chocolate per second. All right. D, the minimum probability that a randomly selected chocolate is imperfect according to the function is 0.0781. State the corresponding rate of production that would result in this probability. So they're saying, here's the minimum. The minimum probability is 0.0781. What's the production rate at that point? What's the x value for the minimum point? G-solve, minimum, what's the corresponding x value? 3.575, 3.58 chocolate per second. Okay, moving on. We'll get this done. E, the manager chooses a new production rate for the assembly line. They claim the production rate will result in the minimum probability that a randomly selected chocolate is imperfect. Okay, calculate p hat, the proportion of chocolate that are imperfect in the sample of 80 chocolate. All right, so p hat is equal to x on n. So we've got 6 out of 80 from the sample. And you can leave it as 6 out of 80, or you can express it as 0.75. Okay, part 2. Assuming the sample of size of 80 is large enough for the central limit to a theorem to apply, determine a 90% confidence interval for the proportion of chocolate that will be imperfect at the new production rate. So, using this, calculate the proportion confidence interval, 90%. So, proportion confidence interval, what are the things we need? We need confidence level, 90%. Okay, what else we got? Our value of x and our value of n. So 6 and 80. So that's the information we'll put in. And the confidence interval we get is this one here, 0.0266, less than p, less than 0.123. I've already rounded it, but that's what we get. Now, last year, if people were putting p hat, we were penalising you, okay? P hat is the sample, right? P is the proportion, and we're saying the proportion of the population lies between these 2 results based off of our p hat value, okay? All right. Using the confidence interval that you've calculated above, can it be concluded that the manager's claim is false? Okay, this is where I really want to talk about testing claims. So the manager claims, what does the manager claim? But they claim that the production rate, so I'm reading at the top where part E, the production rate they have chosen will result in the minimum probability. Okay, what is the minimum probability? 0.0781. 0.0781. And what we can see is 0.0781 lies within this confidence interval. Okay, so two things. The first thing is to answer the question. The question is, can it be concluded that the manager's claim is false? The manager claims this lies within the confidence interval. We can see clearly it lies within the confidence interval. Can it be concluded the manager's claim is false? Answer the question. No. No, you can't conclude that. Why? Because the minimum probability of 0.0781 lies within the confidence interval. Okay, so I want to point out some things that we can say. So that's appropriate there, full marks there. Answered the question, there's your justification. All right. Things we can say. Evidence supports the manager's claim. That's okay. All right. The evidence does. The confidence interval supports the manager's claim. Okay. Things we can't say, very subtly different. Manager's claim is true. We can't say that. And the reason we can't say that is because this is a definitive claim. It's saying what he's saying is true. No, we don't know that it's true. Rather, we've got evidence to support it. Okay? So that's what they're looking for. They were like lots of people would say this kind of thing. Manager's claim is true, and we were picking on it. All right? So it needs to be very precise. Evidence supports or evidence rejects. All right. Okay, very last one, 20 seconds. Now, it says, using the confidence interval you calculated, determine the 90% confidence, the upper and lower boundaries of the new production rate. So we're saying again, what's the production rate that corresponds with these probabilities? Well, the lowest it could be is 0.0266, and there's no production rate. That's down here. There's no production rate that corresponds with that probability. The highest it could be is 0.123, and so that's going to be like here. And so you're saying, what are these values that correspond to 0.123? That's the highest the production rate could possibly be. Here's its lower boundary, here's its upper boundary, and you get 2.27 and 5.52. All right, we'll wrap up there. Then the other one we might do tomorrow. We'll see how we're going. Keep up your revision. Most of the lesson tomorrow dedicated to your own stuff. So I did just want to go over this today. So yeah, good work, and we'll catch up with you tomorrow in tomorrow's